You got a set of vectors V1 through VR. And a linear combination is just a set of sum of multiples of V1 through VR. There it is. If you have an equation, linear combination of this set equal to some vector. Now we're going to notice that we have R of these and N of these, which means we might have more of these than we have these. We might have less. Now, N is what? N is your number of equations, because of course you set this up as a matrix equation. That's, your V1 through VR. If they're going to add up, if the sum of multiples is going to add up to this, then each of these has to have length N. Okay? Because you can't add up a bunch of vectors of length 3 to get a vector of length 4, for example. So we have the equation V1 through VR. This is going to be an M by M matrix. I usually make it M by N, but we typically use N for the dimension of the space. So we have an N by R matrix here. N rows, R columns. Okay. Now, if R is less than N, are we guaranteed a solution? Okay. If R is greater than N, can we even have a solution? Okay. In other words, if we have more equations than unknowns, then we kind of expect we ought to be able to solve it. Okay, but is there an exception? Can you have an equation with more, can you have a system with more equations than unknowns but not have a solution? Okay. Can you have an equation with more unknowns, or can you have a system with more unknowns than you have equations? Can you solve that? And then ultimately, what does that have to do with rank nullity and all this stuff? Okay. So at this point, ideally, we'd be able to sort all that out. But let's talk about this a little bit. Maybe I didn't zoom this, but I was sure that I had. And of course, when I zoom it, it goes out of focus. But it zoomed itself back. Okay, well, anyhow, I understand the question. Okay, well, there's the board for anybody who happens to be looking at it or viewing this. Okay, for the case where, we don't need to see that now. For the case where you have board. Maybe I shouldn't have zoomed as much as I did. Okay, let's stop that. If you have more equations and unknowns, we got a couple really good immediate responses. We discussed this. Okay. And I said it wrong again. More unknowns than equations. I'll keep that up there and take a chance. Okay. Now, if you have more equations than unknowns, that means that I said it. You write it correctly. The why people wanted to write the same thing, but more unknowns. Of equations. Okay, well, how many unknowns do you have? You have R unknowns and you have N equations. So in this case, R is greater than M. And the immediate response that I got very quickly was parameterize. Have an infinite number of solutions, right? Okay, example. Okay, you let x2 x1 equal t, x2 equal negative 2t plus 7/2, I think. Okay. Yeah, pretty sure that's right. Okay, well, that's solution sets a one-dimensional linear subspace of R2. And if you extend this to, you have 6 equations and 8 unknowns, then you're going to get a two-dimensional linear subspace. When you parameterize it, you can separate out your parameters and stuff like you learned to do in chapter 1, right? And then you can express the solutions as a linear combination of 2 vectors that you get, depending on how you parameterize it. With the same subspace, it doesn't matter how you parameterize it, but the vectors that you get will form a basis of that subspace. And of course, the basis of a subspace is not a unique thing. There are many different ways you write a basis for two-dimensional subspace. Now, if it's a one-dimensional subspace, then every basis is going to be any basis you write is going to consist of a single vector. It's a multiple of the single vector you get for any other basis. Okay. Because the line is unique. The direction of that vector up to reversible negative is always the same. All the vectors in any basis, the vectors are going to be parallel to the vectors in any other basis. If you get 2 or more dimensions, that's no longer the case. There are many ways to form a basis of a two-dimensional subspace. Infinitely many. Okay, well, that's kind of perspective. We'll have to have more equations and unknowns. Now, is there any exception to that? Is there any case where you have more equations and unknowns, but you don't get infinitely many solutions? Okay, so we know, for example, if we have the equation 2x1 plus 4x2 equals 7, and 4x1 plus 8x2 equals 10, well, this left-hand side just a multiple of this, double, right? This is double this, but this isn't double this. Okay, so there's no possible solution, right? Now, if you go to 3 equations, I didn't want to write 3 just because of room, but if I had an x3 in here and an x3 in here in this equation, left side was a multiple of the right side, and these weren't multiples, then I'd have r greater than n, but I have a system that doesn't have any solutions. Okay? So there's no x1, x2, x3 that'll make both equations true. Okay, so and since I qualified that and just carelessly wrote 2 equations, let me just make it doubly clear. Okay, now we have a system of with more variables than equations. But parameterizing isn't going to help you because what you get if you let x3 equal t here is going to contradict what you get if you let x3 equal t here. So make sure we understand that. Okay, if you have more equations and unknowns, then what do you expect? Well, let's talk about that. And of course, I wasn't recording what I just said, but we can see it very quickly. Okay, if you got more equations and unknowns, a number of things can happen. And I'm glad I looked back, and I'm glad I didn't record that without noticing. Okay, here's a system of three equations and two unknowns. In general, you expect the coefficients over here to reduce in such a way, and of course I'm doing the augmented matrix, everybody knows how to do this. Okay, if the augmented matrix reduces to this and this isn't zero, then you don't have a solution. So if it's not degenerate, there's no solution. That could be degenerate, could be as people said when we just discussed this very briefly. If one equation is a multiple of the other on the left side, but on the one equation is a multiple of the other on both sides, then you could have a solution. You would expect a solution, at least one solution, maybe infinitely many. So ponder that. Okay. So anyhow, again, if R is less than n, if you just think about what we just did, it's easy to generalize it. There exist B's for which there's no solution because there exist vectors over to the right on that augmented matrix to the right of your dotted line, where when the thing reduces, you don't get a zero. If you get zeros over here, that means no solution. It's also possible that one equation could be a multiple of the other, in which case your system of three equations is just equivalent to system of two equations. In that case, the matrix will reduce and you will end up with rows of zeros, okay? If R is greater than n, then I'm going to say here, there exists, and I think we've used this notation, but the backward capital E means there exists a number I less than or equal to R such that B sub I. Now, what's that mean? Well, you have R vectors. There's some number less than or equal to R such that the VI, well, if I is less than or equal to R, then VI is one of these vectors. There exists some vector in this set that's a linear combination of the others, which is equivalent to saying that there is just a linear combination of your R vectors such that the, well, that's equal to zero, a non-trivial linear combination of these vectors is not zero. If this is so, then that's so. Meaning these things aren't linearly independent, okay? And then I say this is equivalent to saying there's a non-trivial set of vectors C1 through CR such that this equation is so, such that, and this just expresses a linear combination as it did up here. But this linear combination would be zero. In other words, a solution. Meaning the vectors aren't linearly independent, meaning this isn't the basis for anything. Meaning that you have the span of this is less than R. It has dimension less than R. Okay. Now, if R is greater than n, a lot of this is equivalent to saying, and you work out the equivalencies. I'm just going to kind of state this because we need to move on. But if the rank of V1 through VR is n, then the span of these things is V. Okay. Now, does that mean if the span of these things is V, does that mean that we have the V1 through VR is a basis? Let's profound state of the world. Okay. So if people wanted to agree that that would make this a basis, but of course the basis has to be linearly independent. There's no guarantee that this is linearly independent. There's no guarantee that R equals n. Because if R doesn't equal n, this ain't a basis. R is greater than n. If R is greater than n, you don't have a basis, but if this set spans V, you could reduce this to a basis. Just find one of those i's, find your VI that's a linear combination of the others or whatever, or that gives you, well, find an I that's a linear combination of the other, okay? Find an I such that VI is a linear combination of the other, and throw it out. Then see if you have a basis. If you don't, find another one, because there's going to be another one. The rank is n, meaning these things span a space of degree n, which is your whole space, because everything we're talking about here, we're in an n-dimensional space V, capital V. Okay, so again, just start throwing vectors out until you got a basis. Start throwing vectors out until you got n of them. Okay, worth pondering. Okay, now if the rank is less than n, then the span of these vectors is a subspace of V. Now use the proper subset symbol for subspace. That's not necessarily standard, but this is a subspace. You understand my intent. And if you want to clean up the notation, that's fine. But that's a familiar symbol, so I decided to use it here. Okay. Okay, well, in this case, this can be reduced to a basis of W, which is the span. Okay, doesn't mean, again, that the span has dimension R. Because the rank is less than n. Actually, I should have said the rank is less than R, which is less than n. Okay. No, never mind. I didn't say the rank was R. Probably should have used something besides R so I wouldn't confuse myself and everybody else. Okay. So again, this means that this can be reduced to a basis of W, to a basis of a span in the same way this could. Then we have nullity. Of this set is equal to the rank minus the dimension of W. And that's true. I should have used braces here, and this is the nullity of the span and so forth, but you get the idea. Looking at rank, nullity, and dimension. Okay. Want to think that one through. In terms of the system of equations, in terms of augmented matrix, how it reduces, and everything. Okay, so that kind of puts a lot of things together. Yeah, come on. Okay. And the inner product that we express, your text expresses, in you kind of use a less than sign here and a greater than sign here, or I call them pointy braces, okay, or pointy brackets or whatever. That's the notation your textbook has chosen. It's a standard notation, not the only possible notation. There are other notations in use, but it's as good as any. Okay, it's much like V dot W, because V dot W has properties that are just like this. I keep things in alphabetical order. Okay, if this is a dot product, you know it's true, right? Well, when we define an inner product, we think, what are the properties of dot product that characterize a dot product? And now we can call it an inner product if it has the same formal properties. Okay, well, that's one of your formal properties of dot product. Okay. Actually, put this here. I want to put it outside because in either case, it comes outside. It's like a constant does in an integral. And that's going to be important because one of the inner products we're going to see here in a few minutes is an integral of two functions. Okay, integral involving two functions, inner product of those functions, which is a measure of kind of how close those functions are. Okay. Important property is probably the one that's listed first in your textbook. Order doesn't matter. It's like the dot product. Okay. Now there's no, yeah, this is important. The positive definite property. Okay. Now I say unless, and that's not quite right. Okay, because this says if u is equal to 0, then sorry, it says if this is greater than 0, then u isn't the 0 vector. Okay, but it doesn't say that if u is a 0 vector, that this is equal to 0. Okay, so a better statement would be okay. It's an if and only if statement. If u is 0, then this is 0. Okay. And if this is 0, then u is 0. This is called positive definite. I'm not sure your book uses the terminology. Sometimes put this in parentheses and make this a stronger statement. This is a stronger statement than this is. Now, maybe this could be proved using this and all this. Okay. Might think about that, but let's prove something. Let's prove that actually, I think I've misstated something. We're not going to do this. Okay. You read it before. And I don't want to go back and fix my statement. This is close enough. The authoritative set of properties is what's written in your book. They can sometimes be written a little bit different. Okay. So there are theoretical properties. Might or might not have to deal with those in the web assignment homework. I don't think you will. Maybe. Again, the thing acts just like dot product. Okay, so let's just I want to jump to function space here. Let me think of anything else that I was intending to do. some reason, and maybe it's not a good idea to do this, we're going to do that. Okay. Let V be the vector space consisting of all continuous functions in the interval 0, 1. Okay. Let the inner product of f and g be the integral of f times g from 0 to 1. You put a dx in that. I didn't specify the variable, but let's implicitly assume your variable's x. It's not necessary to really write that. Okay, so what's the inner product of x and x squared? Okay, I wasn't recording when I said all that. I thought. If the, well, I think everybody got the 1/4 there, and I'm pretty sure I recorded that just in case. B is a set of continuous, the space of continuous functions of 0, 1. Your scalars are implicitly real numbers. The inner product is just going to be defined as the integral from 0 to 1 of fg with respect to whatever the variable is. So that, and I used the dx here, you just probably wouldn't generally write that here. But since we're going to use x for our variable, I went ahead and wrote the dx on it. So if your functions are x and x squared, what's the inner product of x and x squared? Well, it's the integral from 0 to 1 of x times x squared, the integral of f times q, and that's the integral of x cubed, and that's 1/4. Now, by analogy with the fact that the cosine of theta is v dot w over magnitude of v magnitude of w, which comes from the definition of your dot product as the magnitude of v times the magnitude of w times the cosine of theta. That works real well for vectors, for arrow vectors. We're going to say at the cosine theta, well, just replace the dot product with the inner product. And you get this. Now, magnitude of v, magnitude of w, remember the magnitude of v is the square root of v dot v. Magnitude of w is square root of w dot w. So you are familiar with that. So I wrote it down this way. But now I write it down this way because this is what we mean by the norm of v. Could call it a magnitude if you want to, but magnitude kind of applies to arrows. And norm applies to more general vector spaces. So I'm going to call that the norm of v times the norm of w. Norm of v is the square root of the inner product of v with itself. Norm of w is the square root of the inner product of w with itself. So you're working that out because I failed to record this. We'll see how you do. Okay, so in this case, the inner product of v and w would be the inner product x with x squared. Yeah, okay. So we're still using x and x squared. Let's find that a little better. Over the square root of the inner product of x with x times the inner product, square root of the inner product of x squared with x squared. Well, this is going to be the integral from 0 to 1 of x cubed dx. Then you're going to divide by the square root of the integral from 0 to 1 of x squared dx. And the square root of the integral from 0 to 1 of x to the 4th dx. Now, skip the step because the integral of x with x, or the inner product of x with x, will be f is the x, g is the x, Again, you got f times v x times x, which is x squared. And similarly, if f and g are both equal to x squared, as they would be here, then you're going to have x squared times x squared, which is x to the fourth. And then those integrals are really simple. This is just 1/3, 1/4, sorry, over the square root of 1/3 times the square root of 1/5. Okay. Well, let's note that 1/4 over the square root of 1/3 times 1/5 is 1/4 over square root of 1/3 times 1/5. And that's 1/4 over the square root of 1/15. Well, the square root of 1/15 is a little less than 1/4. Okay. So this is less than because 1/16 is less than 1/15, right? In any case, this is 1, because square root of 1/15 is 1/4. So this says that this is guaranteed to be less than 1. Okay. The square root of 1/15 is a little bigger than 1/4. And it can usually prove that. The same token that the square root of 1/9 is bigger than the square root of 1/16. And 1/3 is bigger than 1/4. You can do an analogy there, or you can do one more. You can set up inequality. I'm not going to do all that. So, among other things, this makes sense. Okay. And for any inner product that satisfies these laws, it's always going to make sense. Now, why does this make sense? Because this is supposed to be the cosine of theta, right? Cosine of theta has to be less than or equal to 1. And so we can prove that for any inner product, the inner product of V with W is less than or equal to the product of the norms of V and W. It's called the Cauchy-Schwarz inequality. This is necessary if we want to make this definition. Now, I'm not going to prove that. I don't think the book proves they just state it. Might be something in the problem section. Also, call this a triangle inequality. The magnitude of V plus W is less than or equal to magnitude of V plus the magnitude of W. Okay, why is that? Well, if V and W are vectors, then it's like you got V here and W here. And here's V plus W, right? So this is the hypotenuse of this triangle. Okay. Magnitude of V is the length of this, magnitude of W is the length of this, magnitude of V plus W is the length of this. Shortest distance between 2 points is a straight line. There. That's for dot products, okay? A little more general, follows from all the axioms. You want to kind of think about why those. It gives you a deeper understanding of the whole concept of inner product and what it applies to various spaces. Okay, well, that's an example of an inner product of, when I saw it, oh, that's pretty neat. Okay. Gives us a whole lot of tools to use. And I didn't even appreciate at the time just how many tools, but I knew about Taylor series and understood how you said polynomials has a basis, 1x, x squared, x cubed, and so forth. And that spans space of all continuous functions. Well, there's more. But let's talk about, I'm not going to talk too much about R2 and R3 and so forth, but I think you'll understand that. I have to work through some examples. Appreciate it. There's some strange inner products. The dot product's not the only possible inner product on real vector spaces. You're going to see examples of that. Maybe I'll get to them. Maybe not. But what I want to do now is look at two different possible bases for polynomials. Or two different possible inner products for a set of polynomials. Let's say okay, V and W just A1x squared plus B1x plus C1, W A2x squared plus B2x plus C2. We define this. That's an inner product. It has all the properties. Okay. V dot W equals W dot V. I'm not even going to write this out. If you reverse these, then you have A2, A1, B2, B1, C2, C1, which is the same. Okay. The only way the inner product can be zero is if, well, never mind. I can't. There are many ways the inner product can be zero. Okay. Inner product is zero means these things are orthogonal. This means cosine of theta would be zero, means theta would be 90 degrees. Okay. And I said that's fast. If you didn't understand it, I'll do it. Okay. And before you. Okay. The other properties are equally easy. The only way V dot V could be zero It's very quick to get this because V dot V would have, instead of A2, B2, and C2, you'd still have another A1, B1, C1, which gives you A1 squared plus B1 squared plus C1 squared. And the square root of that, well, that's your magnitude of V. Okay. So just positive definiteness. One of the properties. Magnitude of V is zero, if and only if A1 equals B1 equals C1 equals 0. And D would be your zero vector. That should be obvious because you have a square root of three things, none of which can be negative. So the only way these three non-negative things can be zero, add up to zero, is if all of them are zero. Okay. Make sure you understand that, otherwise you make something of a mystery and you really don't want that to be a mystery. Okay, so this is a good inner product. I've proven it. I'll say so, for example, it's a positive definite property. I didn't write that down. Okay, but there's one of your properties. We just proved it. The other properties are even easier. Well, I don't know if it's even easier. The other properties are very easy to prove. Also, note that this looks just like the dot product. Okay, if you're in R3 and you have the vectors A1, A2, A3, and B1, B2, B3, the dot product is going to be just that. Okay. Just use our integral definition. Well, that gives us something quite different. Got this integral. Well, you can do that integral. Very easy. You just write it out, use it to multiply these things out. I'll just kind of shortcut it. I get an x to the fourth here, so I have A1, A2, x to the fourth. I get an x cubed by multiplying this by this or this by this. Gives me A1, B2 plus A2, B1. Well, and then I can multiply my c's by my squared terms, and I get something very similar to this. And my x squared, right? And my x's. Uh-oh. I knew I left something off. It's going to be binomial expansion. So I'm going to have three terms. Two. This would be this, because I also get an x squared from D1 from the x. Okay. And then if I just want x's, but then that's going to be that. You can verify it. Might even be wrong. Okay. And then you're going to have C1, C2. Integrating that with respect to X. Well, what do I get? And then there's myself room. But I get, as I have here, A1, A2 times 1/5, right? And this times 1/4. Then it's a little hard to read that. You should know what's going to happen. You can even read this. Okay. And this should have been X squared here. I'm not going to write out the rest. But I want to demonstrate that this is a completely different inner product than this is. It's in some ways more complicated, but it's also in some ways a whole lot more revealing about how close the graph of one function might be to the graph of the other. Their book has some nice examples of graphs. But just one example that I think the book gives it, so let me give another one. Now you should be thoroughly familiar with the graphs of your basic power function. Well, I'm going to do the integral. One's a straight line, and the other isn't. Here's X. Here's X squared. Okay. If you integrate these, you get something that's fairly close to 1. Okay. The product of these is just your X squared. Okay, well, there's 1/3. Okay. Or 1/4. And what I said is, anyhow, if you did X cubed, well, X cubed is a whole lot like X squared, but between when X is 1/2, it comes twice as close. Actually comes, well, you have the point on this graph, you'd have the point 0, 1/4, here you'd have 0, 1/9. It comes much closer to this and flattens out a lot. Okay. So this function is much closer to this one than this one is to this. So if you do the inner product with the integrals and visualize what the integral means, you get some important insights. So I kind of recommend you think about that. Just so you have, again, an idea of a somewhat not intuitive inner product. Makes it a little more intuitive. Now, coming back a little more Monday, because I do have time to do a couple on R2. Let's test. I'll use so let B equal A1, B1, and W equal A2, B2. And my question here, is this an inner product? Okay, well. Is this true? Well, yeah. Because you're just reversing the A1 and the A2, the A1, A2, and the B1, B2. It's clearly commutative. Okay. Is the inner product of B with B equal to 0 if and only if B is equal to 0 vector? Well, clearly if B is a 0 vector, well, you'd have A1 squared and B1 squared, right? The inner product of B with itself would be 2A1 squared plus 5B1 squared. That equals 0 if and only if A1 and B1 are both 0, because these are both positive. Okay. We could do V, or like U, V plus W, so that the thing distributes. Okay, I would leave that to you because we've got 5 minutes. I want to do an example of one that isn't. Okay, but this is a perfectly good inner product. Now we get into linear transformations. You could see you could linearly transform your space so that this thing becomes essentially the same as your standard dot product. It looks a lot like the dot product. It's going to get a 2 here and a 5 here. Again, as you do the problems, think about things like that. Try to develop some insight into how these things work. Okay. Okay, this one's very clearly not going to be an inner product. Well, W would equal this. At the inner product of W and B, you would change each 1 to a 2 and each 2 to a 1, right? And that would be 2A to A1, which is just fine. Plus 5B to B1, which is also just fine. But then it would be minus A2 B1. Make it more concisely. Okay. Not so unless this is so, and then you can, to really complete the proof, you have to come up with an example of an A1 and a B2 and an A2 and a B1, whatever. A1, A2, B1, B2, such a, this isn't equal. I'll just randomly pick A1, A2, B1, and B2 without trying to make them equal. And it's very likely that they won't be. And there are easier ways to pick it too. Okay, also, our book doesn't write it down. Okay. Also, with A1, B2 is much bigger than A1, A2, or B1, B2. Think about how that could happen. Your book gives at least one example. So this can be negative, and that's not good. Okay, there's a couple other concepts that are really important. Now, an inner product space is a space where we have an inner product, vector space with an inner product, because that allows you to find things like distances between vectors, test the angle between vectors, and in particular, it's very important to be able to test orthogonality, which is like perpendicularity. So I'll just mention this. This is between B and W is the magnitude of the difference. Now you've already seen that in the dot product. If you read carefully. Also, in terms of things that I've done here, here's G. And actually from what the distance between them what here. Okay. Then this vector is B minus W. This is B W minus C. The B minus W is going this direction, and the magnitude of the vector doesn't matter whether it's in this direction or this direction. So magnitude of B minus W is just the magnitude of the vector from the tip of B to the tip of W, or vice versa. And that has a direct correlation to length, but it works in the abstract space, like C01. Okay, quickly. In W are orthogonal, which is like perpendicular. If they're in a product of zero. Okay. The cosine of theta is zero because the numerator of cosine theta is the inner product. So theta is pi over 2, 90 degrees are perpendicular. So we call it orthogonal when we're not talking about R2 and R3. In R2 and R3, that means perpendicular. In higher dimensional R spaces, it sort of means perpendicular. So we're going to use the word orthogonal. And when we get into P2 and P3, or P, Pn, polynomial spaces with an inner product defined in terms of the integral, or function spaces, C0, 1. Then you really need to say orthogonal, not perpendicular. Perpendicular does not have any geometric meaning in those spaces. Make sense? Okay, well, I think you should have not much trouble with the homework. If you understand dot product well, you'll have no trouble understanding inner products. Of course, if you have questions, let me know.